distributed around these 5 main blocks, with a big portion of the list of projects under development or under validation. We are now around 15 projects requesting registration or verification, with another 5, and then 5 recent projects that have been officially registered. So one of the goals of this training and this session and future session, as I said before, is to try to move that big box closer to the registration request piece, and then also facilitate the, in the case of BBBs, as the session is today, facilitating the work of during the process of reviewing projects and validating projects. That's the main goal that we're trying to achieve with these sessions. So these are the 5 projects that are currently registered, and as you may have seen in our announcement, one project has started issuing credits. It's the project 5511 in Brazil. So again, this is in the spirit of improving the usability and applicability of the methodology. The context of this session is precisely that: improve our processes, our communication with BBBs and projects, so the process can move faster and but still with high integrity and rigor. So what is a performance benchmark? Let's start with that, the important part of the methodology. So to put everything into context, as I said before, the methodology has these 2 main accounting approaches: the census-based approach and the area-based approach. We are not going to talk today about specifics of the census-based approach, but it's a good reminder that it's another pathway that projects can use when using BM47, and it specifically applies to spores, discrete plantings that occur in areas that do not result in land use change. But the main difference with the area-based approach, or the core difference, is the way we establish additionality in the performance of the project is using the performance benchmark, through the use of a stocking index, which I'll speak in shortly. But basically, the area-based approach is targeting denser or spatially continuous planting. It is mostly estimated through estimated carb stock change using plots, in combination with the remote sensing approach in the performance benchmark, and then scale to the whole area of the project. The core of the performance measurement is the use of a stocking index that is used to compare project and control pixel or plots to facilitate the accounting over time and follow the trends in vegetation through time since the project starts. How the performance benchmark work is that basically the idea is that it avoids establishing hypothetical assumptions in the baseline, because basically we try to track the projects or the business as usual, the baseline, using control plots, with the process pointing to constant updates, at least at every verification, which basically constitute what is called a dynamic baseline. It is based on a matching process, so it's not selection. The pixels are matched between the project and the control plot, so they can better track the changes in vegetation when comparing the development of the project and compared to projects outside, to control plots outside the project. And it's still, the BM47 is anchored in requiring physical measurements, so they can be compared with and correlated to the use of a performance benchmark. So how the performance benchmark works, I think it's important to set the stage in terms of the conceptual diagram and conceptual model of how this performance benchmark works. So the purpose of the performance measurement is to quantify the historic and initial condition of of this unspecified remote sensing metric, which is the stocking index, via time series analysis for a series of representative sample plots. That means remote sensing plots that are in control areas and in the projects. So the process of the performance measurement is to have a look back period that goes as far as 10 years in the project, with different time steps that the methodology requires to capture the stocking index at those times. One between the T-10 and T-8, one T-5, and one at the project start date at T0. So once we have that, we can track the same pixels for the project, and then basically the ratio and difference between these two lines, it was constituted performance benchmark, which is used later in the final accounting of the removals. This is an example of a no pre-existing biomass, sort of a barren soil or clearing or that is clear because of site preparation, but we can have as many curves as initial conditions can exist. So this is an example of a baseline that is showing a degrading forest. Again, we have these 3 time steps of the stocking index, look back, and then we monitor the behavior of those pixels in the project and the controls to establish the performance benchmark. So basically the core step when applying the performance benchmark in BM47 is the selection of a stocking index. So we wanted to show what projects are doing and what we think is a good approach when selecting a stocking index to facilitate how BBBs are evaluating this when reviewing projects. As I said before, the performance benchmark is determined by comparing the average rates of that stocking index between project and control plots. It's important to emphasize that this is a relative measure and of change. It's not a direct estimation of carbon. We are having internal discussion on how in the future we may incorporate some other approaches about direct estimation using remote sensing, but at the moment the focus of the performance benchmark is the stocking index as a relative measure of change and not a direct estimation of biomass. So that's why the stocking index is defined as an unspecified remote sensing metric. This, as long as it has direct correlation or demonstrated correlation, and that means via peer-reviewed literature or data collected from the project area or outside the project in the region that has demonstrated correlation with above ground biomass. There are different indexes that can be used. One of the series of common indices are the normalized different fraction index that can be retrieved using Landsat. More recently has been development around using average canopy height derived from LiDAR, or even biomass models that well, we'll explain later how that could work and how this can be used in the context of the stocking index. It's important again to say that BM47 does not prescribe a specific stocking index. So it's up to the projects to demonstrate that their index or the stocking index they're using follows the methodology in terms of the demonstration of correlation with above ground carbon biomass, and that it can be tracked in both the baseline and the project. That is one of the most important part of the stocking index, because it minimizes the potential for bias because you're applying the same index to both scenarios. Again, it is important, and that's why we are emphasizing here that the stocking index must be the way it's chosen. It has to be thought, has to be able to be consistently measured over time in both the project and in control plots. And the stocking index that is selected is used to derive the time series that I was showing before on the look back period, and then moving forward exposed after the project starts. The demonstration of the relationship, I'm going to reemphasize that it's important to demonstrate that using peer review studies, validation using direct measurement from the project region. So, for example, on the bottom right of the slide, there is an example of people and projects and data service providers using radar, synthetic aperture radar, as a way of creating a stock index that can be correlated properly with above ground biomass in a particular region. And it also is important that to consider that when applying the performance benchmark, that requires all the steps that are in there, and my colleague Spencer is going to explain those in detail in a few minutes. Once you set up that performance benchmark and you select the project, select the control and the project plots, those are recorded and established for the duration of the curating period. So it is important to have that in mind when evaluating the use of the stocking index in BM47 projects. This is a recent example of a project that applied the NDFI, the normalized different fraction index. And in doing so, the project was relatively creative in combination using different data available to capture the dynamic of the area. Through time, in this case, this project used almost an annual time series instead of the only 3 times step, which is the minimum required by the methodology. But given that people can retrieve these indexes automatically sometimes, it helps them to monitor the development of the vegetation. The red box signals the project start dates. In this case, this is an example of the look-back period of a particular project that combine restoration of a degraded natural forest and sustainable forest management with eucalyptus plantations. In doing so, this project tested different ways of combining all the data available to create different aspects and evaluate different models of stocking index. So knowing the age of the stand, for example, was a good variable to incorporate in a model with the stock with the specific index that can retrieve a good results and can meet the requirements of the methodology. Again, the normalized different fraction index is a good example, especially at the beginning of a project, when people are trying to establish how the dynamic of the vegetation can be traced over time. Recently, it's important to recognize that as projects mature and trees mature and grow, most of these reflectance-based index like NDVI or NDFI usually are useful for detecting early vegetation recovery or growth, but they may saturate once canopy closes, and that represents a challenge for projects. So that's why we are now in a phase to discuss how other metrics than the canopy height can be used to facilitate the monitoring of growth across projects. And again, the important piece is that the stocking index is applied consistently to both the project and the control plots. And probably most of you have seen that Verra is moving towards allowing projects to use biomass models provided by specific data service providers. Recently, and my colleague Spencer is going to speak about at the end, we have indicated some data service providers have been vetted because their products and their processes are aligned with the methodology. So this means that these biomass models are basically allowed to as a stocking index for using the methodology. So in this process, for the validation and verification process, it's important when evaluating projects that projects may choose to change and switch models of the stocking index over time, and the methodology contains the specific requirements that are related to that. So, for example, in an initial step for validation, one metric can be used. For example, those NDVI or NDFI indexes can be used, and then the project may choose to change stocking index models for ex-post monitoring. But the important part here is that there should be a line, and there should be some harmonization or consistency in how you monitor the change of the stocking index. And again, the same stocking index metric must be used for both the project and control plots. If projects choose to use a new stocking index, this must be justified, and it's been, whenever possible, harmonized with the previous metrics should they choose to change the metric. This continuity must be documented when projects are deciding to do that. And in version 1.1 in particular, all the project plots and control plot location, including their stocking index value, should be properly documented in the project description. So the process must be transparent. Version 1.0 has a slightly different language that points to projects not needed to include in the project description. So, but in version 1.1, we are aiming at this data and this information to be included in the project description. With that, I think I'm gonna hand it over to Spencer. I'll be monitoring the chat for questions, and please keep, if you have any other question, put in the Q&A or in the chat. I think that's where Tuan indicated. So Spencer, I'll hand it over to you.
Great. Thanks, Emilio, and thanks everyone for joining. I'm going to add on to what Emilio has discussed. And he did a good job of laying out how the stocking index is really this variable that we're using to represent relative changes in vegetation between project pixels or project plots that are remotely sensed and control plots that are remotely sensed. And this allows us to use quasi-experimental design in VM47. So we know what that variable that we're tracking is, and Emilio did a nice job of laying out sort of how we get that and what the suite of possibilities are for stocking index. And what I'm going to talk through is how we get good representation of both the project and control plots. And when we say plots in this case, I just want to clarify, we do mean just remote sensing. There is not going to be a situation where projects are required to do physical measurement of controls. They will have to have physical measurement plots in the project, and those should be sort of randomly distributed as well. They don't necessarily need to overlap with the project plots that are remotely sensed. The physical plots can be just randomly distributed. So you have to keep those two terms in mind. In this case, I'll just be using project plots because it's easier to get out and say, but that does mean in this case remotely sensed. So next slide, Emilio. All right, so how do we go about getting this representation? So the first thing that we're doing is we should have a shapefile for our project area, and then the first step is to divide this area up into it could either be pixels or it could be configurations or aggregations of remote sensing or stocking index pixels. And so in this case, we can see this grid being overlaid. That could sort of be naturally occurring because of the way, or occurring because of the way the pixels and stocking index are set up, or it could be superimposed upon the area. But it's basically a way to divide the project area up and then allow for the next step, which is going to be randomization of selection of those project plots. And so this whole process is contingent upon having a large enough area of this project plot to be really representative. So we do have requirements in the methodology that 75% of each plot needs to be within the project area. We don't want to just get a portion of a project plot. That might throw our measurements off, not really give us a great representation. And then we also want to think about what's the total number of these project plots that we need to capture. In the methodology, we use 30 as sort of the very minimum. That's the floor. If you go below that at any point in the future at a verification event, you're actually not going to be able to credit because there are not enough project plots to represent or accurately represent potential change. So we should be looking for projects that are using quite a bit more than an N of 30 for these project plots. They could use 50, but we would expect to see some attrition. If you see projects that are just using 30, while that's acceptable at maybe validation, I think it's worth probably flagging and saying, you're doing the minimum here. What's maybe asking the question of like, what's the additional cost to get more of these pixels selected so that you don't ever run into a situation where the project, because of either remote sensing errors or cloud cover or whatever, doesn't have enough pixels to observe. So just something to kind of note. I don't know that can be it could be a finding that you just flag and have the projects think about adjusting. It may not be something that you can stop a project from advancing forward, but just something to keep an eye on. And then I think the last piece of this you can advance, Emilio, is just that this is a randomized selection. So you should be checking for some either set of code or a process where they went through and they randomly selected these project plots. So that's really the heart of what makes this a quasi-experimental design methodology. This is the only randomization step in the appendix, and it drives basically all of the other selection. But at this point, this is where we are ensuring that we have randomized samples that are representative of the project area. And then that leads to matching of these control plots. So this is really the keystone of ensuring that we get good random representation. And so there should be a check on that. If they are running this all in a on code basis, then you should be able to have them point out or have them flag what that randomization step looks like. And so I think we can now go to the next slide. All right, so then this randomization is really essential. It helps us prevent like the projects from just saying, okay, we're gonna grab all the pixels that look like they're the least vegetated, and that we, that way we know we're gonna go get control plots that have very little vegetation. This should just be a broad swath representation of what the landscape that they're comparing to is going to look like, and what the project starting point is. Next one. I mentioned this. It is really the foundation for quasi-experimental design. Next bullet. And we talked about the minimums of having 30 or more. I'll just emphasize this again. We're seeing some projects that are using like an entire census. They're taking every single plot or pixel that's within a project area and finding it a match. And so that could be hundreds of thousands or potentially millions of pixels, depends on the resolution. So that's acceptable. That is okay, and probably a really robust way of doing this. You're going to have maybe a little bit more compute. But again, 30 is really the floor on this, and those projects that are sort of in the hundreds, that's maybe that's fine. They might have larger areas. They're getting more of an average, but we would expect this to have pretty wide coverage, and it should be fairly low cost. This is again all just remote sensing. They should be able to have a data set that they're working with, and so just picking up more of these plots isn't, it's not like physical measurement. It's not like adding 20 plots is going to skyrocket the cost. It's really just a computer exercise. So that's another reason for just thinking about looking at the project design and making sure that there's a reasonable number of these project plots. And then this final point is just that in grouped projects, we are expecting that for stratification that you can be adding instances to existing strata, and we're coming out with some clarifying language around this in the next hopefully couple of weeks or months to basically just clarify that instances may be added to strata. You just need to ensure that each of those instances, it may not have a plot, but there should be representation of new instances. Where if you are adding, you need to expand your plots and do the same exercise if there's ever instances being added at future verification dates into existing strata. So we could see that number of instances expand, and we just want to make sure we have clear representation of those instances within that stratification. All right, next slide. So again, this is just talking through the different configurations of what selection of a stocking index could look like. And so it could be at the pixel level. This could be just a single 30 by 30 meter is the coarsest resolution we would allow. It should be 30 by 30 meter or less than that. So we did design that intentionally around Landsat and expecting that some projects may start with, like Emilio mentioned, NDFI or NDVI, where they have these relative indices of vegetative change. Or we could see these configurations of pixels where you might put some together. You might add 4 together, and then you'd actually just be taking the weighted average of a stocking index. So in this case, you might see these 4 Landsat tiles, and you get a NDFI value for each, and you're taking the average of that. And then when you're doing your matching, you're going to be looking for similar matches in terms of what that historical vegetation has been at various points in time. And then this final picture is another sort of way of doing this, where rather than just using the pixels themselves, they're overlaying the circle plot, which is acceptable, and they're laying that on top of their stocking index pixels, right? So then you're just getting the weighted average of each pixel that intersects with this circle, and using that value to inform an overall average of that circular plot. And so those are all 3 acceptable ways to set up your project plots. And then the next steps we'll walk through how we go about matching those. But we want to first give, if you'll go to the next slide, Emilio, we want to first give you just 5 items to look at or think about when you are going through a review. We want to be thinking about our sampling frame. So we want to make sure that we have instances, that all the instances represented in a stratum are, or all instances are at least assigned to a stratum. And then within that, you would be seeing good representation across instances. This, I think it's important to note here that not every single instance needs to have a project plot on it. You could have, thousands of instances that are grouped together, and you may just see, some subset of those that randomly get selected where a pixel falls within a project plot, and that's what's going to, represent that, both that instance and other instances. So just be checking, to make sure that there aren't instances that are sort of outside or not being captured in at least one strata that has a performance benchmark. And I think that's the other important note here, is that each strata should have a performance benchmark. So to represent the project, you could imagine that it's all just one large area and that has one single performance benchmark. That's acceptable. But if you see a project stratifying into maybe different planting types or different interventions, those are likely going to have different performance benchmarks. They may have, different starting characteristics, or they may want to represent what they expect to be different vegetation changes, and so they may want to stratify those. Those need to have 2 separate performance benchmarks for each strata. That could also, stratification could also occur along the lines of planting year. It doesn't have to. Like we are anticipating to make a change that basically allows for multiple years to be grouped. And the way that we basically allow that is that there are tests to make sure that that your measurements are hanging together. So we would rely on uncertainty to look at those differences, and if there's a really big variance or big difference in carbon stock change, then our uncertainty quantification and some of the tests that we'll talk about later should catch those issues. So we do feel comfortable like having multiple annual cohorts be grouped into a single strata. I think that's an important clarification to share with you all, and that we will formalize in our upcoming changes to VM47. And then we talked about the selection of control plots, minimum sample size, project boundaries, and then our acceptable pixel sizes, that aggregation. So these are all the things that you would check just to make sure your project plots look good. All right, next. So once you have your project plots selected, now we're stepping through into the process where we are matching, not selecting our control plot. So we use that term matching really deliberately. We want to make sure that it's clear, that it's not like you get to go out and look at the landscape and say, oh, we think this area is a good, looks good, like a good representation for our project. We're going to go grab those pixels. That's not how it works. We have this randomization of project plots, and then we use a matching process by identifying these covariates to say, okay, we have to match across all of these criteria, and then we're going to use a final step to look at vegetation change over the last 10 years to select up the control pixels. And so this is all sort of algorithm based. There is really no, there doesn't really need to be, human in the loop. Like they just need to, hopefully press go on this, and you're going to end up with a subset of well-represented control pixels. So the things that we're looking at here as covariates are jurisdictional boundaries, so they need to be within at least the same country. We could refine that even further and say maybe it's just within the same state. They should be within the same ecoregion, so a similar vegetation type, and there's more specifics in the methodology about what ecoregion means. They should be in the same policy environment, and that's probably going to is probably going to be very similar to our jurisdictional boundary, but we want to make sure that, like, let's say it's you're seeing people planting on farms. If those farms are eligible to get some sort of incentive for planting, we want to make sure that all of our control plots are eligible for that same incentive, right? And that allows us to say, okay, there could actually be some financial incentive being added to carbon payments. And what we're able to assess then is actually the difference between those. Like we can see these controls that have, basically no carbon incentive, and these project plots that have carbon incentive and whatever other policy or incentive exist within that area. So that gives us a nice clean way to be able to decipher those. They need to be outside of another AFLU project, so that again helps us control for comparing to other carbon projects. Land tenure, so if we have this available, and we recognize that some countries do not have like private land demarcation. So we would actually allow for land tenure to be something, maybe as coarse as, public land and then everything else, or public land, protected areas, and then everything else. And then if projects really want to drill down on this, they could use something like land cover or land use maps where they can, demonstrate that agriculture is, the primary land use for projects. And so they want to use, they want to make sure that they're matching to other farms. And so they may use that map and that layer to add in and say, okay, we're going to make this apples to apples comparison of private land, agricultural land to private land, agricultural land outside. So that would be acceptable, and we are seeing more projects sort of lean into where they're working in data poor areas, lean into sort of developing these maps. They should have good justification for that, but often we recognize that land tenure can be difficult to find. And then the final check here is just the distance from the project plot. So we start with a 100-kilometer radius from the project, and that's just sort of an initial frame for looking at all of this. And we'll talk about if there aren't enough matches, you could go wider than that, but it's our initial starting point. The last thing I'll mention here, and it's sort of related to what I just discussed on land tenure, projects can decide to add other filters into these criteria. They should be reasonably justified. It's not even a PD deviation. It's just like they could add this and say, we think that there's another layer here that is important for getting good matches. And again, it just needs to be true for both within the project and outside of the project, and that you can, within the same region, that you can be able to look at this, any other filter that you're applying to help refine your matches. So that is something you may see when reviewing this step in the project. Okay, next slide, Emilio. So that should give us something that looks, similar to this, right? We have this 100-kilometer radius. We've got all of these control plots that are eligible, and this little black area in the middle, that's our project, right? So we've divided that area into project plots, and now these are all the potential matches, right? And you can see that there's lots out there, right? So we can easily exceed 30 if we need to, and that shouldn't be a problem. We've gone through all these filters, and basically this is the population that we're left with. So how do we go from this to actually having good matches for the project pixels that we have? And this that next step, if you'll go to the next slide. So we walk through that circle, and actually we're going to drill this down even further. This is another example from a recent project, and they've said, okay, well, there's actually this, this might be the land tenure thing. They want to make sure they're comparing to other areas that have the same land tenure. So you could start with that larger circle, drill it down another step, and now you're getting down to just the area that could be the eligible area. So we just wanted to give two visuals, one with the circle and that's everything, and then one where we would have these other filters sort of working and applying and constraining your entire area even further. Okay, so next slide. So then we're thinking about, we've got our frame, our sampling frame, we've got this population eligible. How do we get good matches? And I think the first thing to point out before I start talking through this slide is that we can do a 1-to-1 match of project pixel to control pixel. We could do a 1-to-5 match. We could do a 1-to-10 match. And so in the methodology, we talk about the K value, and that's basically how many control pixels are going to be matched to our project pixel. And so we may have a K value of 10, and that's going to mean we've got these 10 matches, and we're going to go find the best 10 matches for each of our project pixels. Or we may have a K of 1, and we're going to have something that looks more like this. So just for simplicity and ease of understanding and it being able to explain this, we're just going to assume a K of 1 in this case. And so we have our one project pixel right now being matched. And what we're going to do to go ensure that we have a good match is look at 3 time steps in the past 10 years and we're going to start using our stocking index. We're going to use that variable that we think is a good representation of vegetative change. And we're going to start looking at how vegetation has changed at those over the past 10 years. And we're going to say the pixel that has the most similar vegetation trend or pattern is going to be the best match of that from that sampling frame. And so we go and we look at what's happened in our project. So we have, we could imagine if we were using something like NDVI, this could be like, I don't know, 80, and then at time 5, we have a NDVI value of 60, and then we go back to T minus 10, and it's back up to 80, right? So that's telling us something about maybe what the land use has been or vegetation trends there. Maybe it's differences in rainfall. So we're going to now look at our potential control pixels and see which of those has that best has a trend that looks similar. And so we say, okay, our control is actually a little bit lighter. It's 75, not 80. We go back to T minus 4. That's when we have imagery, and we can say, okay, that's maybe 55. So we've got another value, and then we go back to T minus 9, and we have a value that's like, again, 70 there, or 75. So that's pretty close. But when we compare it to these other two control pixels that are, have similar vegetation trends, we would be, thinking about this as, this control 1 is probably the best fit for that. I know this sounds like really manual and intensive, but basically we, again, are just doing this through an algorithm, and we're allowing the projects to pick an approach. So this could be this is going to be done through multivariate distance metrics, looking at these different configurations of what a stocking index value has been and finding the best fit for any given project pixel. So that all should be done, sort of in this automated environment where you're getting those values, and you're basically saying, based on those 3 values, here's the 1 or 3 or 5 pixels that are the best matches for that. So that should then pull that in and give you those matches. And we're gonna, if we go to the next slide, we're gonna have something like this where we're thinking about what's happening in this green box. Like what happens over on the right side of this graph is what happens in the project after project start date, after all of our matching. That's great. We can think about that later. But right now, what we're really saying is like, how do we get these matches to be a good fit for our project? And that's what we just walked through. You could imagine that this is just a one-to-one match, and so we've got these crosses that represent our project, and then these circles that represent our controls. And so now we're gonna now that we've got these matches, we can observe over time what happens. And this is really again, why this matching process is so important, is because we're going to use this to, again, be our representation of, if there was no carbon finance, what would have happened in absence? And we want to make sure that our comparison points are really representative of what would have likely occurred. All right, so next slide, Emilio. So this is just, again, another representation of, we could think back to that circle with all the dots. Like, this is that same circle, but with all of those dots represented by a stocking index. So you can see this really wide variance and some of this like cohesiveness around where we see, what the stocking index values would look like. And we want to go through this process again of this is just another visualization of how we do our matches. So each of these red crosses is a project plot, and then we're getting these clusters of, it looks like they're doing a K of 5, so they're matching 5 of the closest control plots to each of those red plots. And at this point, they'd stopped, like they just had ran 30. They could have, it looks like maybe they could have gone up to 50, and this is, again, just a visualization. So let's say they're going all the way to 50. They just stop at 30 to kind of do a check and see how their control plots are looking. At this point, you're also, since they are getting, we are getting potentially more than just a one-to-one match, we want to add some weights. So we want to weight these control pixels based on how well they match. So we want to give those pixels that are the best fit, they look the most like our project plots, we want to give those controls the most weight. So there is a weighting process in the methodology. You'll kind of see this embedded there, where basically we're using those multivariate distance metrics to assign that weight, and then use that then to average and get a control stocking index based on those weights that we'll use to compare to our project plots in the future. Next slide. So then we're matching. Actually, I went too fast. Go back one. So once we've done our matches, we also want to check that we also have a good standard difference of means. So there is a step here where we would be looking at each of these and saying, okay, what's our standard difference of means? The covariate that we're using to do that is this stocking index, right? And so that's why it's important that we get these averages, that we get an average for the project plot and that we get an average for the control plots, right? And so if you have this, this match of 5, you need to get that weighted average from that, right? So that's going to be the thing that we do have a test for, to make sure that our project and our control plots are a good match, and that we have a standard difference of means of at least 0.25. All right, so next slide. Here's everything basically that we just talked about. This is your checklist, and we anticipate having something like this available in the near future to be able to share, so that we're all basically looking at the same things and looking looking for the same things. So these are our donor pool delineations, control plot eligibility, all of our filters, our stocking indices for these different time points, our matching, like how many, what's our K values, our weights, and then our final standard difference of means is our final test to make sure that those, control plots that we ended up with matches look like they're a good fit, are going to be a good fit over time. Next slide. Okay, so this is another just visualization of what that can look like, and we cover standard difference of means here, but again, like this is how we might think of, this looks like a K of 7, right? So we've got our projects plots here, and then we've got at least 7 matches, and if I'm miscounting there, apologies, but we've got our matches to each of these project plots, right? So that's what we're going to be looking at over time. I think you can go to the next one, Emilio. So let's say you get to that step, you run your standard difference of means, and you exceed your standard difference of means value. At that point, we might actually need to go and rerun this process by expanding the circle and saying, okay, there's got to be better matches out there. So the first step would be to run to add another 100-kilometer circle out so that you can expand that population. So if if you see that starting to fail, another option might be looking at those matching criteria and thinking about, is there maybe a finer resolution or a different way of grabbing that data and just making sure that you're still getting all of those criteria, but either loosening or constraining, whichever the case may be, needing to find another way of getting those matches dialed in. So that's, again, an opportunity where a project proponent might think about another layer that they want to add in and say, well, we think that there was a lot of noise because we were getting commercial land in there, and that's not really going to be a good match for our project, or they may just need a larger sample to go choose from. But we haven't seen this issue yet, but I expect that at some point it could come up. Okay, next one. All right, so this is sort of our final step to ensure that we have our control plots matched, that we've, again, just gone through this process. We can sort of pick it up again here at our standard difference of means, that we've rerun this, make sure that, you know, you've added another 100 kilometers, or maybe there's been another data layer inserted to refine that. And then we have our final controls. So this is something to really pay attention to, I think, in project proponent data, that you have a database of all of the both project plots and all of the control plots, and clearly assigned like which of those control plots belong to which project plot. So there should be clear and easy way to cross-check that and say, okay, this is control plot 1 for project plot 6, right? So you should have some way of demarcating that and making sure that we have then all of these weights, like what's the weight for that value or that control. And then we should also have a physical location for that. And then the other piece of the database should be that you have a stocking index value using the stocking index that they have selected. So if they have NDVI, they should have those at least 3 historic time points, time 0, T1 to T-8, and then T-8 to T-10, right? So you should be able to see all of that in one line and say, okay, this is a control plot. It belongs to this project plot. It has this weight. Here's its location, and here are its stocking index values, because that's going to set us up for success whenever the projects move then to verification. And then, yeah, we also have some replacement logic. So like I said, it's possible that a project comes to, you know, to verify, and they have to drop pixels either because their project plots are masked with clouds, or, you know, maybe there's something that that happened that, you know, they need to remove that, or it's also possible that they have lost control plots, that some of their matches are either no good, or maybe there's another carbon project next door, and so they need to remove that. So that would sort of invalidate those processes, or invalidate those matches. So we should be checking for a process in which they replace those. They could either, you know, replace the entire thing, or if they need to replace just a control plot, they should be able to do that as well, just using the same process, making sure they're getting an adequate match. All right, next slide. And this is, again, just an example of a project that we, that's, I think, been validated, and they have 150 project plots, 450 control plots. So doing my math really quickly, that's a K of 3, and it's right there on the screen. And so, you know, basically this is our stocking index value. This is our comparison of above ground biomass. They have a stocking index that, you know, looks like it's going to work, or going to get them started at least for this project. And so again, we can kind of see this, like, you know, you don't see a perfect circle here for our matches, and that, I'm going to guess, is probably based on just the one of the filtering criteria. So maybe they're trying to match private land, and what's to the right or the east here looks like it might be a protected area. So that's not going to be a great fit. And so everything that they're selecting from is in the upper left. And so they've been able to go and pull those plots, and now they're ready to start observing change in the project. Next slide, Emilio. All right. So here we're starting to think about moving into verification, and once we have these matches that have been validated, then starting to use these matches to observe project and control plot stocking index values. So we set our matches. Now we're really ready to put that into action. So Emilio's touched on a lot of this, but we want to make sure that we have our initial stocking index values that should all be represented in some sort of database. that were using this same stocking index metric. So they shouldn't be using, and we get this question occasionally. A project will be like, well, we can get LiDAR for the project, but it's going to cost a lot to get LiDAR for the control. Can we just use it for the project to represent stocking index? And the answer to that is no. We need it in both project and control. Like, that's how we make sure that these are, that we're not over crediting or under crediting based on a stocking index error. We think if we have it in both, then it should be a good representation of relative change in both project and control areas. We also are then looking for our project plots are fixed, so they're not moving. So and we should have locations for those as well. And then same goes for our control plots, that those have been fixed. We have their weights and their locations. And then I think everything else here we have already pretty much covered. So we'll be compiling these lists into something that has everything all in one place, that you could be able to look at a full set of a project's approach to this, and be able to just go down the list and check things off and make sure that we're all on the same page. All right, next one. So the final step here is, we've got stocking index now, we've got our control plots and our project plots matched. Now we're moving into how do we make sure that we can use those observations in the future to credit. So what are we looking for? So now we're thinking about basically the slopes of these lines that are associated with stocking index change in our population of project plots, comparing to the slope of the line in the population of, or the selection of, our control plots. And so we're going to have these two lines that are hopefully, clearly, have a clear direction or have a clear value. And we use a z-test to make a comparison to basically say, are these lines, are they showing a different slope, and are they showing enough of a difference for it to be attributable to the project intervention? And so that's our significance test for the slopes of these lines, is the z-test. And that gives us, Emilio, if you go to the next slide, that gives us something that looks like this, where we've got our project slope here in the solid line on the right-hand side, heading upward, up and to the right is our project slope. We can see that little representation of what our stocking index is within the project, and we've got our representation of what the control is in this dashed line here at the bottom, or in the sort of middle of the screen. And so, we would be thinking about, does our z-test tell us that the slopes of these lines is significantly different? And so we're going to run that, and we're looking for a value less than 1.96. And so that should indicate to us, if you want to go to the next slide, Emilio, that the slopes of those lines are significantly different. And so I might have got that wrong. So where the z-test, the z-score is less than 1.96, there is not a significant difference. And so that would not be an eligible, that would not be enough of a difference to be able to credit the project. So if a project fails that as they're doing a verification, then they're probably just going to have to wait. And we do see this as a sort of a potential challenge for projects. Like with some of these stocking index metrics, it may just be that they're green enough to be able to say, or not be able to detect the change due to new growth in the project areas. And so they may not see those slopes really diverge until several years down the line, and they may be really anxious to get credits out. So it's possible that this is a really important check for us to make sure that they have significant difference in their project and controls. I also want to note that if we see projects that are failing this, one of the things that they may be asking us about is it possible to update to a new stocking index? And based on what Emilio discussed and what's in the methodology, yes, they may go and use a different stocking index value. They may want to update from this NDVI to something like a canopy height or an above ground biomass model. And those are totally appropriate stocking indices. However, again, they just need to be used both in project and control. So they could do all of their matching using NDVI or another a more core stocking index. They have to keep all of their matches and their locations based on that, and then they can update and use a new stocking index when they go to do verification. It just needs to be applied both in project and in control. And so they may, decide that they want to do that, and that, that allows them to detect enough difference and have a different slope in their lines because of those observations. To us, that's acceptable because you're still making an apples to apples comparison. You're comparing the same stocking index and changes in that stocking index, and it may be more sensitive, so it's picking up those changes. So we really do want to see this check on the z-score, and where the z-score is greater than 1.96, we would expect that to be a significant difference, and that gives us our final step in using the stocking index to basically make, if you want to go to the next slide, Emilio, basically make this, turn this into a factor in our carbon removals equations, right? So this is where we have all of our accounting based on project plots. We're going to figure out the delta, the change in carbon stocks, and then we're going to adjust that removals based on 1 minus the performance benchmark, right? So where we see a negative slope to a line based on these stocking index values, we just set that to 0. If we didn't set that to 0, then we'd be potentially crediting reductions, and we don't want to be doing that in this methodology. We want to be extra conservative and just say where the performance benchmark is negative, we're gonna adjust that back up to 0. So that's that min function that you see, and then where it's a positive value, then we would be taking that as our deductions in the performance benchmark. So in this case, performance benchmark of 0.54%. That's going to be our deduction 1 minus 0.54%. So that's going to reduce. It's going to be a fairly small deduction in that case, and we're going to be seeing that sort of subtracted out from our carbon stock. So that's how it all sort of gets wrapped back up into the methodology and adjusts crediting. Next slide. So again, this is our sort of final look at what we just talked through. So once we have our controls, and once we're observing stocking index in those controls, what are all the things that we're looking for? We have our time series, we have our control weights, we have our project weights, we're getting our slope calculations. We do have a standard error calculation that's included in there, and then our z-test to make sure that the slopes of our lines are different, and then that we're applying our performance benchmark appropriately in the final step. All right, so I think that's hopefully enough content, enough of a deep dive into how we set up our performance benchmarks and then how we operate them using a stocking index. We want to talk a little bit about a couple things that I've mentioned in this presentation and that Emilio has touched on. So we recently just announced this vetting of data service providers. So we were getting lots of questions from project proponents about, we're gonna try and use this stocking index. We're gonna try and work with this data service provider. Is their data eligible? And that was leading to a lot of back and forth. And we were learning a lot about the data products that are out there, which has been really awesome to see that these groups are putting together these data sets that actually work really quite well often for stocking index, but rather than having to do this on a one-off basis, we decided to create a process for data service providers to come to us and do a pre-vet. So basically show us their process for all of how they would either create the stocking index, so doing the check to make sure that it's whatever stocking index that they're using or model that they're using is associated with biomass, that they have all of the ability to basically randomize and select project plots, do the control plot matching processes, like that can all be that process can all be checked up front. And then once we've looked at that, we'll post their name onto our website and say, these are vetted. It doesn't mean that you don't have to check this, especially if you're a VVB or a verra reviewer. Like, you should be looking at this in the context of the project, making sure that their processes are being adhered to and that they're adjusting them appropriately for the context that they're working in. So it's not sort of a hall pass to get around this. It's just sort of giving confidence that, yeah, in general, the approach that they're using for creating stocking indices and the performance benchmark would be eligible, assuming that that's all sort of checked during the review process. So that list will be on, or is on, our VM47 webpage, and you can go and see which data service providers have applied, and we are expecting, we're already seeing more come to us and say we want to get our process vetted. So we do think this will help give confidence to both project proponents and some of these data service providers as well. But yeah, if you have any questions about that, we'd be happy to answer that. I think the takeaway here is just that it's still your job to have to check this, check their processes. You could see that they're vetted data service provider. You could look and read what they, or you can see what the process they use is, and then you should be able to kind of compare that to what's in the project as well. And then next slide. These are some of the updates that we anticipate within this year coming out. So I've mentioned a revision to VM47. This is really just to get in alignment with BCS version 5.0, and we expect this out in Q3 of 2026. So there will be some changes in there, but they're really all sort of focused on changes that were made in the standard in the last version that was released in December. We're going to release the long-term average tool, expected out in Q4 of 2026. There will be a public comment period on this, hopefully in Q2 or Q3. And then a harvested wood product tool that complements the long-term average tool. And then finally, a transition procedure for projects moving from AR-ACM or other AR methodologies to VM47. So there's going to be a more structured guidance that we're providing to projects that are interested in making that transition to VM47, and that guidance document is expected out in Q3 of this year. So hopefully that's some those are some good things to look forward to, and we'll hopefully do more sessions like this to answer questions, probably in a public setting as we release those pieces of work. All right, so I want to pause and see what questions you all have. I'm sure Emilio's been working on that in the chat, and happy to answer those together live here.
Yeah, thanks, Spencer. That was great. I've been trying to respond to as many questions as possible. I chose a few that will be useful to discuss live. You touch on the replacement of plots, and basically when you were addressing that part, I think you responded to sign up question, but I'm going to ask it here. If some randomly selected plots are later found unsuitable due to cloud cover or image quality issues, can replacement plot be selected? And yes, what procedures should be followed?
So I think there's two distinctions here to make. One would be if it's an issue of cloud cover, it may just not be eligible for that time step or for that verification. And so that's where it's important to probably have many more than 30, but we could imagine a scenario where you have to kick that one out because you don't have a good representation of stocking index. And so you'd kick out that entire match, right? You'd kick out the project plot and the control plot, and either of those could have cloud cover, right? So you might just remove that one and say, that's got cloud cover for this year, we're going to take that out. So you may have gone from 50 now to 49. And so that's still, you could go back at the next verification, and that matching set could be moved back in. You have imagery for it. It doesn't have to be entirely removed. So that's sort of one scenario to keep in mind. Like it may be that some of these kind of ebb and flow, and that some of those matches are just going to drop out, and then they'll be able to move back in at a future point in time. If a control plot is deemed ineligible, let's say in that scenario of a project or another carbon project coming into the area, and it happens, they happen to know that it happens to land on you have the shapefile for that project plot, and you say, well, that's now ineligible. That would mean that you do need to replace that control plot. So you could go back through that matching process. You probably already have a number, if you have a K larger than 1, you would just say, okay, what do we need to replace? And you probably need to reweight based on that. So you could run it just for that single set of controls and get 5 more, and maybe the same 4 that you have, and then you find a 5th that's a good match. And so that would be, I think, the ideal process to replace. I imagine that we're going to see lots of variation in this. Like, I don't want that to just be like, oh, that's the only way to do it. I think what we're really looking for is like, does it look like they're, is it sort of a one-off thing? Does it look like they have a reasonable solution? A lot of these data service providers that are, much more, I would say, technically astute than myself. And so they may come up with a good way to say, okay, we're just going to, pull that out and we're going to replace it. And here's what we did to do that. I think what's important is that we just check that process, make sure that it's following these same principles of randomization if they're selecting project plots, and then matching through these sets of criteria on the control plot side. And so as long as it's looking like a similar set of processes, I think that's totally fine.
Yeah, thanks, Spencer. Here's a question from Ananya, that I think is important. I think is somewhat related to the cloud cover limitation in the stocking index, but in this case, it's about mortality. Like how to address mortality during the validation and subsequent baseline reassessment during the verification. Like how does mortality should be addressed when addressing the project and control pixel matching, and how this will affect then the certainty estimation.
Let me respond, and then if there's follow-up or if you have another thought on the interpretation here, Emilio, feel free to jump in. So I guess what I would say is, like, if there's mortality within the project's plot, then what you're gonna see is probably a weaker representation of vegetative change from the stocking index, right? So let's say they've gone out, they've cleared, so that's going to be sort of a reduction in NDVI or whatever your stocking index is. And then you plant and you get this like maybe little green up or slight green up happening, and then it dies, right? If there is a project plot, and I mean remote sensing in this case, like that sits over that, then that's not going to show us very much vegetative change, right? And so in that case, you would have done all your matching based on this historic criteria. And then maybe in the control plots, you're actually seeing some sort of vegetative, it could be, I don't know, agriculture or Swidden agriculture, or you see this increase in greenness, and then there's a slight decrease, and then there's an increase again. Like, basically that would give you 2 data points that are saying like, well, our control plots are actually kind of greening up a little bit more than our project plots. And so what that's going to lead to is a plot that exists to reduce the slope of your line in your project, right? So like where you have mortality, that's just going to weight, it's going to reduce the slope of the line for that project plot, right? Especially where you have 2 time points. And if you have this point down here, it's going to bring that line ever so slightly, towards flat. And so I think that's the intent of, the dynamic performance benchmark, is saying like, yeah, it needs to look at what's actually happening on the ground, or a representation of that, and reflect it in this stocking index. The other side of that is that you're going to get a representation, and hopefully equally random sample, of what's happening in those physical plots, right? So if it's just a one-off, and that plot or that area didn't do well, and the rest of the plots are doing well, then your physical plots are going to represent that carbon stock change. And that's great. You're going to see that in the carbon removals. And then maybe you don't even have that represented, but it's showing up in your remote sensing. That's part of the noise. And yeah, there is going to be some of that in uncertainty, or in the test that we have around standard difference of means, at least for the back-looking period. And then moving forward, I think that comes out in our standard error tests. So that's, I think that's kind of the variance that we're hoping to capture.
Yeah, I definitely agree with that. I think it depends on the selection of the stock index. Should be able, once you select it, should be able to capture that variation that is induced by the mortality, and that then the performance benchmark value will change accordingly, and then you will be using that in the calculation afterwards.
Yep.
I like this question. Leo asks whether BM47 expects the performance benchmark analysis to use individual match control plots in the weighted regression, or whether weighted average synthetic control SI values are also acceptable. Whether weighted average synthetic control stocking index values are also acceptable.
I guess I don't know what the weighted average so let me try. So when we were talking about our weighted average of like a project plot, we can either have a pixel, we can have an aggregation of pixels, or we can have an aggregation of pixels with a superimposed like circle plot, or it could be a square, or whatever plot we want. So you could take that weighted, and that's another good point. Like, you should be making a similar comparison. So you should either be comparing pixels to pixels, or aggregations of pixels to aggregations of pixels, or aggregations with a plot overlay on them, both in project and control. So those should be, that should be part of the matching, is that you're using that same aggregation. I don't necessarily maybe know what they mean by the synthetic part of this, but I would say that yes, those like weights and the way that you're doing your selection of project plots needs to be the same for your control plots.
Yeah, I just quickly text that if there is any follow-up, please reach out and we will try to respond on more properly. I have a question here from Justin, and I think we're almost in the time limit now, but I will read it. Per the Appendix A 1.5, the parameter table for the stocking index, the comments describe requirements when a project changes their stocking index metric. Can you elaborate on what a harmonization procedure looks like? Are there best practices that a BBB should be looking for a project to adhere to? For example, are there metrics that a BBB should look to determine whether the new metric is more accurate? I presume this means the new metric is more sensitive and appropriately sensitive to the changes in biomass, for example, such as a greater correlation coefficient.
yeah, that